Hi everyone. So let's continue in the next chapter about primes and unique factorization. So we have the following problem. Okay. So we know that given any integer, we have itself as well as 1, as well as negatives of those things are factors all the time. So we can ask the question, what about those particular integers where those things are the only factors and we arrive to primes as we all know? So let's write that down first. So every non-zero integer n except plus minus 1 has at least 4 distinct divisors. And those are one, negative 1, n, and negative n. So if an integer has only those as divisors, then we call the integer prime. So we have the following definition. An integer p is said to be prime if p is not equal to 0, plus minus 1, and the only divisors of p are plus minus 1 and plus and minus p. So what's interesting about this, as we'll see, is that if a number is not prime, so that means it has factors other than those 4, other than itself and 1 and the negatives. So that means that it can be subdivided into products of 2 numbers. And so you can test if each individual number is prime, and you can keep doing this process until you arrive at the number being broken down as multiplication of prime numbers. So you can see that prime numbers are like the basic building blocks of numbers. So there is one exercise which shows that there are infinitely many distinct primes. So it's not. So remark there are infinitely many distinct primes. And because we've seen that an integer has the same divisors as minus itself, so if we have a number is prime, then its negative is prime as well. So you have the following remark, that p is prime if and only if minus p is prime. And another thing in our analysis process here is the following: if p and q are both prime, where p divides q, then because q is prime and the only factors of the primes are 1, -1, and itself and negative itself, so it can, since p is prime, so it cannot be -1 or 1, so it must be plus or minus q. So then p, as q is prime, then as q is prime, we must have p is equal to plus minus 1 plus minus q, and that's it. But since p is prime, then p is not equal to plus and minus 1, so therefore p is equal to plus or minus q, and we're done. So the next thing is the following theorem. Theorem 1.5. It tells you let p be an integer with p not equal to 0 and plus or minus 1, and then p is prime if and only if p has this property. Whenever p divides BC, then p divides B, or P divides C. So let's prove this result. So first of all, what is the core idea here? So the core idea is that if you have a prime, then that prime cannot be factored further. So then if it appears somewhere in a product, then it must appear in one of the products, right? Because here it's not like we take the two integers p and c, and then when we multiply them out, we introduce new factors. That's not possible. Like, there is no jumps in the integers. So since there's no jumps in the integers, we get that their atomic structure, so to speak, cannot have jumps as well, as everything is increments of 1. So those are the main ideas. So let's see what's going on. So how can we prove it? So let's go in the first forward direction. So if if P is prime, and it divides BC, consider D, which is GCD between P and B. There's two options for that. Why? Well, the reason is that the GCD is bigger or equal to 1, and P cannot have factors other than itself and 1 if they are positive. So that means that D is either 1 or the number P. So if D is equal to 1, then you have, by the previous corollary that we proved before, so then by previous result, we have that P divides C. Option 2, D is equal to P, and then P divides B, and we're done. Okay, perfect. So yeah, so that's the forward direction. Let's now prove the other direction. So assume that assume that P has this property, and we prove that P is prime. So in order to prove that something is prime, we have to show all its factors are either plus minus 1 or plus and minus itself. So let let K be a factor of P. And then you can write P as the multiple of K multiplied by R. So then you have that P divides K times R. Then what this tells you is that P divides K or P divides R. So by the property that it satisfies. This is by assumption. So you can replace P by K. So if P divides K, then P is equal to K times alpha. So therefore, K times alpha is equal to K times R. So therefore, oh wait, P divides K, no. P divides K, then that means you can write K as P times alpha. Then replace K by P times alpha. Times R. So therefore, alpha times R is 1. So R is equal to plus and minus 1. Because, why is that true? So let's show that. So R here is less than and equal to 1. And it is an integer. And R is in Z, which is not 0. So then we must have that R is equal to plus or minus 1. And if R is equal to plus and minus 1, so then you have, if R is equal to plus and minus 1, then you must have that, you must, let's see, so D is a factor of P, such that P is equal to K times R. So then K must be plus or minus P. And and also vice versa. If P divides R, then you can do the same argument with R. Then K is equal to plus and minus 1. And R is equal to plus or minus P. So the only factors, since we started out with a random factor of P, and we've shown that all its possible options and all the possible options of the other factor is either the 4 options of the primes. So then we get that this number is prime, and we're done. So let's see the following result. It says every integer n except 0 plus minus 1 is product of primes. Yeah, so let's start dissecting the idea in the next video. But the main core of things is that if you pick a number, pick its factors, then if the number is not prime, then one of its one of its factors is can be if a number is not prime, then it has factors other than 1 and itself. Then you look at those factors. Since it's not 1 and itself, then you can keep breaking those numbers apart, and then you end up with getting things that are products of primes. And the reason this process doesn't go on forever is again because the well ordering axiom. And the main core reason comes from the fact of that all the integers are just increments by and decrements of 1. So yeah, so let me end the video here and we'll start discussing more next time. See you guys.